Hey, my name is Arjun Verma, and this is my third lab report. So the purpose of this lab is to model the motion of objects under the influence of a net force. And we're going to be doing this by utilizing the momentum principle, Newton's second law, combined with the concept of parallel and perpendicular forces in order to model the motion of a certain object. So our relevant formulae are the perpendicular/parallel forces formula. So the first one describing how the parallel force is equal to the change in momentum over time, or the difference in the change in like the momentum magnitudes multiplied by p hat, whereas the perpendicular net force is equal to the magnitude of the momentum multiplied by p hat over time, the derivative of that. And then we're also going to be using Newton's second law such that F net is equal to dp over dt, or the change in momentum over time, and the gravitational force formula where F is equal to big G m1 m2 divided by r squared. And these will all be very relevant in tracking the motion of our object. So the first thing we did was construct model 1, and the purpose of model 1 was to show an object orbiting around another one and display the parallel and perpendicular and the net forces on the object, as well as determining the mass of the black hole that the object was orbiting around. So first I put in the relevant numbers such as the mass of the star and my email seed, and then from there I utilized the definitions of the change of velocity and momentum in order to find the delta v and delta p variables. Then Newton's second law was utilized in order to find F net. As you can see, F net equals dp dt, or the change in momentum over the change in time. And then from there I found the parallel aspect of the force by finding p hat, and then the difference in the magnitude of the momentum, and multiplying that together and dividing it by the change in time. And since F net is equal to parallel force plus perpendicular force, we could just subtract the parallel force from F net to find the perpendicular aspect of the force. And from there, we knew that the only net force acting on the object, or the star, was gravity, right? So we could set F net equal to big G times m1 times m2 over r squared. And by simplifying that out, we found that the mass of the black hole, or m2, is equal to F net times the r squared, or the star's position squared, divided by the mass of the star times big G. And yeah, that was it. So the results of this are good and they work. You have the net force pointing towards the black hole because that's where gravity is pulling it in, the perpendicular force pointing orthogonal to motion, and the parallel force pointing in the direction of motion, the perpendicular being the blue arrow, the parallel being the red. And the mass of the black hole is accurately corrected at calculated at about 1.87 times 10 to the 34th kilograms. And yeah, our F net, F parallel, and F perpendicular can also be seen there. All of those are in newtons. So what we want to see and what we're exploring in model 1 is the difference between net force and parallel perpendicular forces, and the change in momentum, or the rate of change in momentum, and then parallel and perpendicular forces. And effectively, by Newton's second law, they're the same thing because F net's equal to dp over dt. However, depending on the situation, it might be easier to calculate the rate of change in momentum and set that equal to force instead of doing vice versa or directly calculating force, right? Because in this situation, we couldn't directly calculate the force because we didn't know the mass of the black hole. But since we had our momentums, we can find the rate of change in momentum and then find force that way. And that's where that distinction appears. So model 2 was a similar idea where we were having a planet and a ship orbiting around a black hole. However, now we knew the mass of everything, so we could use the gravitational force formula to model the net force on the planet and the net force on the ship due to the other bodies and gravity. And then from there, we could find the change in velocity and thus the change in position, so we could map the position of all the different objects as they revolved around the black hole. So in order to get my spaceship to come close to the black hole and then escape, I gave an initial velocity of negative 7.7 times 10 to the 7th, negative 1.2 times 10 to the 7th, and 0. And that was after a lot of trial and error, seeing the spaceship go in many different directions. And as you can also see, the planet is accurately orbiting around the black hole. And the what if of model 2 is how could we create something to where the spaceship could somewhat orbit around the black hole. And in order to do this, I tried to get the spaceship as close to the black hole as possible while minimizing its x velocity, such that once it got into the black hole, it'd be inclined to stay in there. And this is just the only relevant portion of my experiment, where as you can see, the red line comes close to the black hole and kind of starts to orbit it for a small period of time. And I achieved this with the velocity of negative 3.7 times 10 to the 7th, negative 7.7 times 10 to the 6th, and 0. And yeah, I had to reduce them in order for that to happen. I had to reduce the y velocity and then kind of increase the x velocity. And that's how it all came together. So it kind of slightly orbit the black hole. Yeah, that is it for this lab. Thank you so much. And yeah, that's it.